There are several ways you can approach graphing trigonometric functions using the basic graphing techniques that we developed earlier in the course. Things like shifting horizontally, shifting vertically, stretching or reflecting, compressing horizontally or vertically. But I have a way that I like to explain how to graph a trig function that I think is pretty straightforward. I hope you'll find it to be so. What I like to do is note the pattern of the graph. And I noted this earlier in a video. Pick out a cycle of sine or cosine, whomever you're graphing, and identify the key characteristics of it. And one thing I identify here about the graph of sine is that I can identify a cycle that begins when the original x equals 0 or ends when the original angle x equals 2 pi, and that's one full cycle. If I can figure out where the graph we were considering, y equals 3, sine of 1/5 x, actually begins and ends, then I can use the symmetry for sine to kind of fill in the gaps there. So let's take a look. Here's how I like to approach it. I like to use a substitution type process. Okay, before I deal with the vertical stretch that's on the outside, you always deal with the stuff that happens on the inside. And so I want you to notice that instead of x, we have the angle 1/5 x. If 1/5 x is equivalent to the beginning position of sine of x, then we can solve for the beginning position of sine of 1/5 x, and this solves out nicely to 0, so no big changes there. Likewise, I can find where the graph ends by setting the argument of the function, or the angle, 1/5 x, equal to where sine is supposed to end, and I find out that this guy ends at the position 10 pi. So it is basically horizontally stretched. So think of it as taking a slinky and stretching it way out, okay? So basically your period, your new period, will be the distance between where you end minus where you began on the number line, or 10 pi units. Okay, now we know that if we start at 0, we'll have an x-intercept. That's how sine, the cycle we've chosen, behaves. If we end at 10 pi, we'll have an x-intercept. And then we can go to the middle and intercept, left to right, middle a high, left to right, middle a low. Okay, so keep that in mind, and let's sketch the graph. Okay, this won't be to the same scale, but we want to get a rough sketch and then look at the multiple choice selections, and I'll try to help you decide which one is the appropriate one for the graph. Okay, so one thing I want you to notice is that we're going to begin at 0, 0. We're going to end at 10 pi, exactly halfway between sine's beginning and ending. We get another x-intercept. Now, halfway between 0 and 5 pi is actually 2.5 pi. And from left to right, because we didn't do anything other yet than deal with the horizontal compression or stretch that's inside, in this case it's a stretch, we still go up to a value of 1. Okay, halfway in between these two guys, okay, so right here, and what's halfway? 5 plus 10 pi divided by 2, so 7.5 pi. We have exactly a low value of -1, and that's the basic stretched out graph, okay, and that is without the vertical stretch. So this is just sine of 1/5 times x. Now, I know that if I stretch by 3, vertically I have to multiply all the y coordinates by 3. So all the x-intercepts would stay the same, and basically what would happen, and I'm going to fudge on my scale here, is that you would multiply 1 by 3 and negative 1 by 3. So your graph should go up to 3 and come back down through the axis and go down to negative 3. Okay, so y equals 3 sine of 1/5 x, should have a high of 3 and a low of negative 3. Okay, now remember we discussed amplitude was actually half the total height of the graph. Okay, half of that height here would be 3 units. Okay, or you can say max minus min divided by 2. Note that that's consistent with the vertical stretch. Okay, for the period, measure where you ended, which was 10 pi, and where we began, which was 0. So our period is 10 pi. Okay, I suggest, even if you have multiple choice problems, that you graph the function by hand and sketch it out to, horizontal scale, and then look at your choices. So let's pause for a second and do that. Okay, now we have before us the graph we just obtained, which is the correct graph. And you see some of these curves looking like several different scales. So one thing I want you to notice about our correct graph is that our x-intercepts occur for our cycle that we picked at 0, 5 pi, and 10 pi, but what we mean is that we have an x-intercept every 5 pi units. So if you have a graph, for example, whose x-intercept isn't 5 pi or 0, 0, then we're going to rule that one out. Okay, so this one's ruled out. All right, now we're going through 0, 0. If I had gone backwards with my graph, it would have come back down here. Okay, so you want somebody that is going from left to right in the negative region, increasing and then decreasing. Okay, this guy decreases and then increases, so that's not the right graph. All right, this guy has a 5 pi intercept, a 0, 0, a negative 5 pi. It goes from increasing to decreasing just like we want, so that looks very promising. Notice that it goes up to 3 and down to negative 3. Well, this one also goes up to 3 and down to negative 3, but this one has many more x-intercepts than our graph is supposed to have. So this is not the right choice, and that guy must be it.